Okay, in this video we start looking at the financial applications of the stochastic calculus we've developed in this course. And the basic idea is that to model the value of a financial asset, we use, well, L2 log stochastic processes. Right. And more often than not, the value of a financial asset won't be given explicitly through a formula that describes the process, but only implicitly through a SDE. So it would be given by, as the unique solution of an SDE of the form dxt equal mu txt dt plus sigma txt dbt, and the class of processes we can look at, therefore this class of values of financial assets we can look at, is constrained by, well, needing to be in L2 log, because that's where our integration theory works, and really being a solution of such an SDE, so an SDE with mu and sigma satisfying the assumptions of our existence in uniqueness theory. But that's a wide class of processes, so that allows us to describe as random variables evolving over time the evolution of the value of quite a range of financial objects. Now, the nature of those financial objects from a legal point of view or a finance point of view is not our concern, right? The XT might be modeling the value of cash in some bank account. It can be modeling the value of holding a certain number of stocks for a certain company. It can be modeling the value of an insurance product or other form of contracts. The nature of what creates that value is not part of the mathematical theory. The mathematical theory just describes how this value evolves over time. And we might know the value at times x naught, right? That's typically the price of buying such a thing. But what we want to know is how it evolves over time. And more often than not, it's not going to evolve in a deterministic manner. We cannot predict what the value of a stock is going to be a year from now as a number or as a function of time, but we can describe it as a stochastic process, so as something that has some level of uncertainty. Nevertheless, to understand what we're trying to do here, modeling the value of financial assets with stochastic processes, it's good to go back to the simplest example. And the simplest example of an SDE is an ODE. Right? It's the case where everything is deterministic. So what if we look at the case where mu tx is just equal to x for all t and for all x, and sigma tx is just equal to 0 for all t and for all x. Okay, then what our SDE is, it's really an ODE, and actually let's say x times some number r, and then let r be some positive number. Then we're really looking at the ODE dxt equal rxt dt, and we know that the solution is xt equal x naught times exponential rt, just from standard ODE theory. And what does that model? Now that models the value of cash in an account returning interest rate, so with compounded interest corresponding to the parameter r, in an account with continuous time interest rate r. Right? If you leave a principal x naught in a cash account and your continuous time compounding interest is r, then after t unit of time, the value of your asset is x naught times exponential rt. Right, this is a continuous time analog for those of you who may not have looked at interest accumulating before. It is really just a continuous time analog, of course, of what happens if you have x t equal x naught times 1 plus r divided by n times t. That's if you have discrete time compounding with period and with n periods. right? So typically, I don't know, if you compound your interest every month, and t is the number of year, then n will be 12, and you have this annual rate r, and then really what's happening every month is that the value of your capital is multiplied by 1 plus r divided by 12, because you accumulate r divided by 12 times the principal in interest. And the idea, of course, of continuous time compounding is that you take the limit as n goes to infinity of that, and that gives you exponential rt. Right, but here we don't want to have discrete difference equations to describe anything. We want everything to be in continuous time. So we are going to use ODEs and continuous time compounding to describe the evolution of the value of cash in a safe account with a fixed interest rate. So this type of equations, these ordinary differential equations, are the most basic equation describing the evolution over time of the value of a financial asset. They are deterministic equation. Here it's a risk-free asset if we assume that the interest rate doesn't change over time and is not something that carries any uncertainty. Now, in real life, you might want to make the interest rate a stochastic process itself, because it can change over time and it can change in a way that you do not expect. But that depends on the nature of the, say, cash account in which you've put your money in. Right, so this very simple ODE is the most basic example of the evolution of the value of a financial asset given by an SDE. In that case, the SDE reduces to an ODE. Now, we can have a more interesting example. Let's have a look at one. So we could also look at some equation like this one. We could be looking at dxt equal rxt plus sigma dt plus sigma xt dbt, where r and sigma are two positive parameters. If we do that, what we're going to have as a solution is not something that looks like this, what we had in example 1, where at time t you reach naught times exponential rt, but what we are doing by making the ODE more complicated and looking at an SDE is that we're adding uncertainty to this description. So what we're going to have as a typical solution is a Fourier differentiable curve that looks like this. It might globally follow the trend of the black curve from example 1. That depends on the value of sigma, but it's going to have some variation around that, and the level, the strength of this variation will depend on how large the parameter sigma is. If you remember, in the previous chapter, we've actually solved that SDE explicitly, and we found that xt would have to be equal to x naught times the exponential of r minus sigma squared over 2 times t plus sigma bt. So what you can see here is that as long as r is greater than sigma squared over 2, you sort of lose a little bit of your interest accumulation compared to the deterministic case, but you don't fundamentally change the behavior. But on the other hand, if the uncertainty is really high, if sigma squared over 2 is greater than r, then here you start having something negative, and the behavior changes quite dramatically. So what I've drawn in this picture is really a case where I have r still greater than sigma squared over 2. In fact, what I've drawn here, where you really essentially follow the black curve, is a case where sigma squared over 2 is negligible compared to the r. So this is really just a small perturbation, but you can have large perturbations too. So this model already is good for modeling quite a large range of financial assets, just picking the r and the sigma appropriately. And remember that we had trouble, and it gets a little bit more complicated if you didn't have here a multiple of xt. It's very natural to have a multiple of xt, because it means that the uncertainty that we're adding is really not just a Brownian motion, which would be of whatever size it is, but this would not be sensitive to whether the value of xt is roughly $10 or roughly $1 million. So it's really reacting, this term here, to the value dxt over xt, right? The idea is if r were to be 0, and just assume that they can be 0, then dxt over xt would be sigma dbt. So the thing that would be evolving like a multiple of the Brownian motion would not be really the value of the financial asset, but the relative changes of its value, right? This quantity here is something like a 10% change in the price, or up or down. This would be modeled by a Brownian motion. So this equation in example 1, the equation just right here, will be used to describe riskless assets in the models we'll be dealing with later on. And these very simple equations, which solution is what we call a geometric Brownian motion, they will be used to describe the values of stock. So they're kind of the simplest versions of the SDEs we've been discussing before. And of course, you can get more and more refined models. You can describe the value of more and more complex type of assets by using more advanced SDEs. Okay, so we model the value of financial assets using our favorite type of stochastic differential equations. So equations of this form, utxt dt plus sigma t xt dbt for two functions mu and sigma that are uniformly Lipschitz continuous with respect to the second variable, uniformly in the first one. Now, in practice, you can use that for forecasting, but this really gets you into the field of statistics. What you want to do is, given concrete data, you want to identify the right model. You want to find an appropriate function mu and an appropriate function sigma that best fits your data. Even if you assume a priori that mu is linear and sigma is linear, you still have to identify those numbers, r and sigma, from the data to fit a good model. Now, once you have a good model, you can use that for predicting how the value of the financial assets you care about is going to evolve. But that's not what mathematical finance is about. Mathematical finance, as a subfield of mathematics, is interested in the following question. If I have two variables, two processes x and y, they both satisfy a certain SDE and they are linked together somehow, how do I infer in properties of one from properties of the other? So this is a very powerful technique to find information about a complex financial asset, something like a derivative product, something that's a function of the values of other assets that you understand better, from information about the assets that you already understand well. And there's one, and just one, economics principle that really makes this approach effective, and that's a principle called no arbitrage. So what is this principle telling us? If I put it in mathematical terms, it tells me the following. Now you have two processes, xt, yt. You may or may not be giving them in terms of an SDE, so implicitly, or maybe you're giving them explicitly. That doesn't matter. What the no arbitrage result tells you is that if you have two such things and they model the value of some financial asset, now, if you know that these two processes agree at one point of time, then they agree at all points of time. So if x at the time capital T is equal to y at a time capital T, then at time 0, say, they're going to have to be equal. And even more generally than that, they're going to have to be equal at all values of the time parameter. Now that seems very surprising. And indeed, this is not a mathematical principle at all. In general, you can have processes that agree at one point of time and disagree at every other point of time. But the fact that they model financial assets is what makes that possible. And what is the idea behind this? So the idea behind this is that the meaning of this equality, that x of t is equal to y of t for some time capital T, I should have fixed that. The meaning of that from an application point of view is that the return or the payoff of owning the asset xt at time capital T is exactly the same as the payoff of the asset yt. So at the point of time capital T, it doesn't matter if you own 1 unit of x or 1 unit of y. They may give you They may pay out a lot or they may pay out little. These are random variables. You don't know what they're going to do, but they're going to be random in the exact same way, right? So if x of t for a particular choice of the probability variable omega gives you 5, then y of t gives you 5. So if these two things give you exactly the same things at time capital T, now could they have a different value at time 0? Well, the answer is no, because let's just imagine that at time 0, y is cheaper than x. And nobody should be buying x. Because if you buy x at time capital T, you're going to get the exact same thing as if you had y, except at time 0, you paid more to get x than to get y. So it would be irrational to buy the most expensive one when there is a cheaper version that has the exact same payoff at time capital T. So if people are being rational, then the product that's more expensive will completely disappear from the market. So if x0 were to be greater than y0, yet at time t they're the same, then nobody should buy x and everybody should buy y. And reciprocally, if x is the cheapest, then everybody should buy x and nobody should buy y, and anybody who has y should sell it immediately. So this means that there's only one rational value of x and y at time 0, or for that matter at any time before t. If they're going to match up at some point, then they have to match up at every point before that. If not, there is something irrational about buying the most expensive one for the same payoff in the future. Now, that doesn't mean that in practice you don't have people who accept buying something for a higher price than they should. And that doesn't necessarily mean that the whole markets break down because someone manages to sell infinitely many copies of the most expensive one and use that to buy infinitely many copies of the cheap one. But in fixing rational prices, in agreeing based on a mathematical model on what the rational price of a asset should be, the price at time 0, x0, well, if I know that my x of capital T is going to be a y of capital T at some point t, then my x0 has no other choice but to be equal to y0. That is the no arbitrage principle upon which our theories are built. So what does a typical theorem in mathematical finance look like? So the fundamental theorems of mathematical finance, they often come under the name fundamental theorem of asset pricing, look like this. I'm going to give you the generic form. You give yourself a family of financial assets, or more precisely, a family of processes that describes the value of at least 3 differential financial assets. Now, you can deal with a lot more than 3, but 3 is the minimal number where such a principle can be applied. So we'll just deal with 3 for now. So you have 3 L2 log processes, and they model financial assets, or more precisely, the values of financial assets. Okay. And you have a maturity time, some point in the future. And now you assume that at that point in the future, z of capital T is equal to some function of x of capital T and yt, or more generally of the entire process up to this point. So you have a certain way of defining the value of z at time t from information on the process x and y up to that time. So we say that z is a derivative product. So you have the products y and x, the two assets y and x, and they have their own values, but the values of z can be derived from the value of x and the value of y, at least at that maturity time capital T, right? So you have that equality, and you assume that, and you assume no arbitrage. So there's various forms of non-arbitrage, but the way we assume it is that because z of capital T is fixed, if z of capital T is equal to some other random variable v of capital T, then the processes z and v would have to be equal for every point of time. And so what the theorem then gives you, so it gives you that there exists a process A and a process B in L2 lock, such that when you consider V of t defined as A of t times xt plus B of t times yt, then you have the following. You have that this is such that on the one hand V of capital T is equal to Z of capital T, and that makes the process V of t what we call a replicating process. V is replicating Z. All right, it has the exact same payoff at the maturity time capital T. And second of all, dVt, the variation of the value of V, is A of t times dxt plus B of t times dyt for all t. And that's what we call a self-financing condition. So the theorems, all these fundamental theorems of asset pricings, they're all of that form. You give yourself some financial assets, they most likely satisfying some equation. You know that one of the assets' value at maturity is a function of the other assets up to the maturity time. You assume some form of the non-arbitrage principle from economics, and then you can find what we call a portfolio. So you can find a linear combination of x and y that replicates z in the sense that it has the exact same value as z at time capital T, and therefore by non-arbitrage it will have the same value as z for all t, and it's self-financing as in it satisfies such a SDE linking an SDE for V to an SDE for X and an SDE for Y. Now, why is that so helpful? So it is very helpful because, let's do that in a different color, 1 implies that V naught is Z naught by no arbitrage. Okay, so what does that tell me? That tells me that I can find the rational price of Z at time 0 by computing A0 times X naught plus B0 times Y naught, right? You remember that this is A0 times X naught plus B0 times Y naught. So if I know the value of X at time 0 and the value of Y at time 0, and I know these processes here that are part of my theorem, then I know what the price of Z at time 0 can be. So typically what you do is you have X and Y be some reasonably simple assets. We will see in the fundamental applications we'll do later that we'll take X to be just the value of a cash account given by the OD of example 1. We'll take Y be the value of a stock given by the simple SD of example 2. And Z on the other hand will be a derivative product, some reasonably complicated contract that depends on the value of cash and the value of stock. And what we're finding now is what the price of that contract should be at time 0 if everybody is being rational. And we'll deduce that from information that we have about the value of X and the value of Y at time 0. Okay, now secondly, and that's also very important, it doesn't just give us V0, because no arbitrage tells us that Vt is Zt for all little t between 0 and capital T, and it gives you a V of t explicitly. Now this is this A and this B, this choice here, that tells you at a time t how much of X you should have and how much of B you should have. That's what we call a hedging strategy. So what this tells us, combined with 2, is that you can construct a portfolio at time 0 in the following way. So let's say you've sold the asset Z to someone. Now that carries a risk. You got some money from selling Z at time 0, but at time capital T, Z will pay off. Maybe it doesn't pay off very much to the person you've sold it to, or maybe it pays off a lot and you owe that person a lot of money. That depends on what Z of capital T does as a random variable. Now, if you want to protect yourself against that risk, all you have to do is buy A0 units of X and B0 units of Y at time 0. Then, as time passes, you just rebalance the amount of X you've got and the amount of Y you've got according to the strategy. So you want the amount of xt at times t to be exactly at, and the amount of yt at times t to be exactly bt, given by beta. It's a certain number, positive or negative, that describe a quantity of something. So in doing that, you have a certain portfolio where the respective proportion of x and y changes over time, but this portfolio is self-financing. So what does this condition 2 means? It means that Vt costs A0 x0 plus B0 y0 and nothing else, and nothing more or nothing less. So what that means is that the evolution of the value of V is only a function of the evolution of the value of X and the value of Y. Now this might be going up or down in all sorts of random ways, and you just keep changing the amount of X, so the number of units of X that you have, the numbers of units of Y that you have, but you do not add money, you do not buy new X's or new Y's by adding money, adding value to your portfolio V. And you don't take values out of that portfolio. So you set up the portfolio at time 0 by buying A0 X naught and B0, sorry, A0 units of X and B0 units of Y. And then you just rebalance that thing using, you know, if you decrease B, you use the decrease in B to increase A, and if you decrease A, you use that to increase B, but at no point do you take value or add value to the portfolio V. That's why we call it a self-financing portfolio. Now, that means that if you are able to rebalance your portfolio, rebalance your spreadsheets where you know how much X you own and how much Y you own at any point of time, if you do that continuously, according to the strategy that the theorem gives you, then you own something that's going to have the exact same payoff as Z at the end of the time interval, right? So it means that if you've sold one Z and you bought one portfolio V, then you will get, no matter what the probability variable is, it's not just in expectation, it's literally you will gain 0 and lose 0 at time capital T. Whatever you might gain from Z, you would lose from V, or whatever you might lose from Z, you will gain from V. So this does two things, right? This sort of theorems, mathematical theorems, that tells us that there exists a specific linear combination of X and Y that replicates Z and that satisfy this SD2, gives us in practice two things. It gives us a way to find the only possible rational price for the process Z on the one hand, and on the second hand, it gives us a replicating strategy. It gives us a way to just buy and sell units of X and Y in order to completely hedge the risk represented by Z. So that's why this is so helpful in practice. In the next video, we'll see the simplest example of such an asset pricing theorem, and this will be what we call the Black-Scholes-Merton model. It goes back to a 1973 papers, and it led these authors to receive the Nobel Prize in Economics in 1997. Now, their work looks at a very simple SD for X, that's the SD of example 1, where you just have a cash account accruing some interest, a very simple SD for Y, where you have a geometric Brownian motion describing the price of one stock, and then a Z, which value at times T is based on the price of a stock. When you reach maturity, you get a certain payoff depending on the price of the stock, and the type of Z we'll look at is what we call a European option. And what the Black-Scholes model does for you is that it gives you the only possible rational price at time 0 for such a European option, and it gives you a replicating strategy to hedge your risk, but also to compute the price of that option at time 0. So we'll see what an European option is. We'll see the SDE that X and Y are supposed to satisfy and what it means in terms of financial assumptions. And then we'll solve the SDE. And solving the SDE, we'll find the process A and we'll find the process B. We'll explicitly construct the replicating strategy, and from that replicating strategy we'll derive the price of the option and the formula that gives that price, which is referred to as the Black-Scholes formula in finance.